Oh, yeah. My apologies. Should have it like that all the time, really. Right, so this was the example I left you with last time. I'll just adjust the lighting to something suitable. Is that acceptable for seeing the board, I mean? You can't see the board. Really? I think you're messing. Can you? You can see what's on the board, can you? Ish. Yeah, but like everybody just goes to sleep then. Okay, so this was an example of a triple integral. Okay, this is an example of a triple integral, so integrating over a volume region. And so the setup was we were given a sphere. So we have to think of a sphere of radius A. Think of it centered at the origin. Yeah, I didn't say that. Centered at the origin. But the density of the sphere that the material is composed of is inversely proportional to the square of the radial distance. So it's very dense down at the center, inversely proportional to the square of the radius. So it's proportional to 1 over the square of the radius. So down near the center of the sphere, it's extremely dense. Its density tends to infinity as you get closer and closer to the center of the sphere. But as you go out away from the center of the sphere, the density decreases like k over r squared, where k is some constant. And so if the sphere is out to radius a, we'd like to be able to express the mass of the sphere. So it's going to come out as some kind of function of k, we expect, because k is some parameter there measuring the proportionality. And we expect the answer to depend on a as well. Because we're talking about a sphere, there may be a pi in there somehow. So we'll be expecting some kind of expression involving pi, a, and this proportional constant k. Okay. Now, I'm not going to wait for everybody to take that down because we did that last week. But I'll get down all the details in what I do out on the page now. Okay. So I'll just switch over. So it's example 2 from last time. So we want to work out the mass of sphere of radius a, whose density is inversely proportional to the radius squared. So the density of the material depends on the square of the distance from that location in the sphere back to the center. Okay. So we'll think of the sphere centered at the origin. And the density is k over the radius squared. So the radius is x squared plus y squared plus z squared. We're doing this as an example to illustrate the change of coordinates. So changing from, I'm going to present the thing originally in Cartesian coordinates, and then we're going to transfer into polar coordinates. Small. Okay. So there's the sphere. So then the mass. The way this is calculated is we do a triple integral over the sphere, and we integrate the density. And we can express this very generally to just say we're integrating over the sphere with respect to the volume element, which in Cartesian coordinates, this becomes integrating over the sphere, the density dx, dy, dz, because the volume element in Cartesian coordinates is just the product of dy, dz. But now, this integral would be kind of quite awkward to carry out within the Cartesian coordinate system. For two reasons. One, the region that we want to integrate over, i.e. the sphere of radius A, it's not easy, the Cartesian coordinates aren't ideal for describing the spherical region. Okay? It's going to bring in the square roots of some of the squares of the various coordinates. The spherical coordinates is a much better system, you can tell by its name, a much better system for describing things to do with spheres. And secondly, the function we want to integrate, which is the density function, that function, although we can see it defined in terms of x, y, and z, and it has a straightforward enough definition in terms of x, y, and z, but it's 1 over the sum of squares. It's going to be awkward to integrate that. And because it's equal to the radius term, so in spherical coordinates, that density will be expressed as k over r squared. Much simpler in spherical coordinates. It's just one square variable in the denominator. Okay? So this would be more approachable. Look easier, kind of, in we expect in spherical coordinates. Okay, so I introduced spherical coordinates to you a few weeks ago. I'll just quickly go through the definition of them again. And what we'll have to work out first, before we can dive straight into the integral, we'll have to work out the Jacobian determinant. Okay? The Jacobian determinant is involved in the volume element of spherical coordinates. Okay? So a quick recap on the spherical coordinates. So we've got our x, y, and z Cartesian coordinates that we're familiar with. And the point up here, I think at this point is hovering up in the, z twice, is hovering there in the positive x, y, and z octant of 3 dimensions. So this point, while this point has coordinates x, y, and z, you can also describe it in polar coordinates. So that is, to describe it in polar coordinates is to talk about the radius r of the point, so the distance of the point from the origin. We talk about the azimuth angle, theta, which is this angle made by the perpendicular projection of the radius down onto the xy plane. We're looking at the projected radius. The bottom of this triangle, this dotted line here, that's the projected radius. Project the radius down onto the xy plane. Well, the angle that makes with the positive x-axis is theta, and the other angle is this angle up here, which is phi. That's called the zenith angle. You have to be a little bit careful. There's no universally adopted fixed notation system for these. In different books and within different disciplines like engineering, physics, maths, there are little local conventions. So in particular, you will see the spherical coordinates described with theta being this angle up here and phi being this angle down here. It's just different people describe it in different ways. So there's no set way to describe it. So if you're ever reading something and spherical coordinates pop up, you kind of have to just double check what they're using, which labels they're using for what. Okay. So the transformation equations for these, which we'll need to work out the Jacobian. Okay, put these down before, but the z coordinate is the most straightforward. That's equal to r cosine of phi. Now the x and y coordinates, the quantity r sine of phi. So you get all these transformation equations by examining the triangles in the picture. I haven't finished x and y yet, so I'm going to add more factors on. That quantity r sine of phi, that's the length of the projected radius. So this r sine of phi here, that is the length of that projected radius. Because phi is also this angle here, by equivalent angles. So r sine of phi is the length of that bottom side of that triangle. So then x will be r sine of phi cosine of theta, and y will be r sine of phi sine. So that describes the relationship between Cartesian coordinates and spherical coordinates. So now we complete the translation of the integral up here, which is kind of quoted in terms of Cartesian coordinates. To spherical coordinates, we will require the Jacobian determinant. So to transform the integral, we need the Jacobian determinant, which is delta xyz dxyz dr theta phi. You have to set down an ordering of these coordinates because that determines the ordering of the rows and columns in the Jacobian. Okay. So by definition, let's write this over dxyz dr theta phi. Remember how we defined these things? It was the matrix of partial derivatives, and then we take the determinant of that. So we've got dx dr, dx d theta, dx d phi. So the old variables, the variables on the top of the Jacobian notation, they index the rows, and the new variables index the columns. So we've got a row with all x's, then we've got the second row with all the y's, dy dr, dy d theta, dy d phi, and the third row is all the z's, z dr, z theta, dz phi, and it's the Jacobian determinant. So we're taking the determinant of this matrix. It's a 3 by 3 determinant, so we have to tread carefully. We don't want it to turn into too much algebraic work. So we'll want to use properties of determinants. So this is a good, we're still working on Stephen's question on the factorizing that general 3 by 3 determinant. And I'll be illustrating some of the principles behind simplifying determinants here. Okay, so all of these 9 entries here come from just taking the relevant partial derivative of one of these transformation functions. Okay. So just push that into there. So what's that going to look like then? So you just differentiate each of the transformation equations according to whatever the variable is. So dx dr is going to be sine phi cosine theta. Dx d theta now, so differentiating x with respect to theta, and you're differentiating the cosine theta part, you're going to get a minus sine theta. So it's going to give you minus r sine phi sine theta. And then dx d phi, well, there you're differentiating the sine phi part, which will differentiate cosine. Okay, so that's the top row of the Jacobian. Let's do the same thing for the variable y as we go across. Any questions, or just shout out or stop me if something you'd like me to clarify. What's the top row? The next row, dy dr is going to be sine phi sine theta. Dy d theta is going to be by theta is going to be r sine by cosine of theta. And dy d phi is going to be r cosine of phi sine theta. The z row is a little bit simpler. Dz dr will be cosine of phi. Dz d theta, well, the z variable has no theta. Think of our point in the diagram there. If you imagine that point, if you keep r and phi fixed and just vary theta, you just get the point kind of spinning around the y-axis like this, spinning around the z-axis like that. So the z-axis, that the height of this point, the point at the tip of my pen here, the height of that isn't changing as you vary the angle theta. So dz d theta is 0. The height doesn't change as you vary z, as you vary theta. Dz d phi, that is, dz d phi comes out as being minus r sine phi. So, that's it. So that's the Jacobian determinant that we want. Now, what we're reluctant to do at this stage is to expand it out straight away, okay? Because it's 3 by 3, there'll be loads of different products, and it would be a very, very long expression, very hard to have a to understand it as a whole. So, but there's a lot of there's a lot of similarity between columns and rows there. So we'd look to exploit some of the properties of determinants. So in particular, the key property that if you see a common factor in any row or column, you can factorize it out. You factorize each term in that row, take out the factor, and the factor comes out, and it's now multiplying the whole determinant. So you factorize determinants by taking common factors out of individual rows or individual columns. Now, looking for common factors here, we see a fair few of them. So down this column, there's a common factor of r down that column there. And down the middle column, there's actually a common factor of r sine theta. They may say, well, hang on, there's no r sine theta there in 0, but there is, because 0 is divisible by everything. So anything can be considered a factor of 0. You can divide 0 by anything non-zero. So in total there, we've got a common factor of r in the third column, a common factor of r sine phi in the middle column. That means we can extract all of that, and it comes out as r squared sine phi. R squared sine phi, and then we have the simpler determinant. So the first column is unchanged. Then the middle column is a bit simpler, sine theta, cosine theta 0. And the third column is a bit simpler as well, cosine phi, cosine theta, cosine phi, sine theta, and minus sine phi. So that's by factorizing the second and third columns. Now, you can just check that there aren't any more common factors around. There don't seem to be. So maybe now we kind of have to go ahead and just expand it out. But you're going to have loads of cosines and sines multiplying each other, so we'll be looking for any known expressions that we can use to simplify the resulting determinant. Okay. So we've got r squared sine phi, and we should certainly either expand it down the middle column or along the third row, because they both have 0 in them, and so that will leave us, we'll only have two 2x2 determinants to work out, so that will simplify that. So let's go along the third row for this. So it's going to be cosine phi times this 2x2 determinant up here. This is right. I won't expand out that determinant yet because I can see a simplifying step doing it. Cosine phi, cosine theta, cosine phi, sine theta. I don't need the middle cofactor because I'm multiplying it by 0. Then I have the third, but minus sine phi times, this time it's the 2x2 determinant in the upper left. So it's sine phi, cosine theta, sine phi, sine theta, and then sine theta, cosine theta. So I'm not expanding it all out yet, just trying to keep control of the thing, because when I looked at those 2x2 determinants, I saw, well, I can see common factors in there, some of their relevant columns. Sorry?
It should be minus sine theta when you take out r squared sine phi, I think.
Oh, yeah, the top there. So I took out, yeah, so I should have left behind a minus sine theta. Thank you. So I should have left behind minus sine theta there. That's the one, isn't it? So that would leave behind minus sine theta there, and then minus sine theta. Yeah, cheers for that. Okay, but in those 2x2 determinants, you can see common factors again. Because there's a common factor of cosine phi in the second column, so I can now write this as cosine squared phi into minus sine theta, cosine theta, cosine theta, sine theta. And there's a sine phi common factor in the first column of the second one. That's minus sine squared phi into cosine theta minus sine theta and sine theta cosine theta. That's interesting. This is nice. It's kind of cosine squared minus sine squared. But when you expand out both of those 2x2 determinants, you get, well, you're going to get minus 1 from this determinant. Because you get minus sine squared theta minus cosine squared theta. And from this determinant, you're going to get plus 1 when you expand that out. In this bottom left 2x2 determinant, don't you here? So you'll get minus sine squared theta minus cosine squared theta. So sine squared theta plus cosine squared theta is 1. So if you minus them both, you get minus 1. Yeah. And this second one here, you got cosine squared theta minus sine squared theta. So it's cosine squared theta plus sine squared theta. So you get plus 1 to the second. So the first one you get minus sine squared minus cosine squared. So that's minus 1. So in total then, we've got r squared sine phi times minus cosine squared phi minus sine squared phi, which is minus 1 then in this bracket. Okay? Minus cosine squared minus sine squared. So the Jacobian seems to come out as minus r squared sine phi. So it was quite a long calculation, but we tried to keep the 3 by 3 determinant contained as much as possible. So we didn't go and expand it out into its huge long expression. We tried to do the factorizing work, without explicitly expanding them as much as we could. So that brings us back to our integral. We'd now like to continue the transformation of it. So we've got the Jacobian. We've got the original description of the integral in Cartesian coordinates. Okay. So we're ready to do the transformation now. So we can say the mass integral will transform to, so we're now going to write it out in terms of the spherical polar coordinates. We're still doing a triple integral over the sphere. The next line will describe the limits of integration for that. And the density now becomes k over r squared, transforming that into the polar coordinates. So remember, the density was k over x squared plus y squared plus z squared. So x squared plus y squared plus z squared is the square of the radius. And then we take the absolute value of the Jacobian, which is minus r squared sine phi. And then we have the three differentials of dr, d theta, d phi. So the present, remember I explained a couple of lectures ago, the presence of this absolute value of the Jacobian there, that accounts for the fact that the r, theta, and phi, they measure distances differently depending on how far away you are from the origin. That's the presence of the r squared here, and what the zenith angle phi is. So for instance, if you think of, so you can kind of get a feel for why this factor here is sine phi. If you're at a point with a very low phi angle, which means you're at a point very close to the z-axis, yeah, a point which is almost vertical. So the phi angle is very low. And when you vary the azimuth angle theta, you're just spinning, the point just spins around and describes a very small circle. Okay, so phi is very low. Varying theta just varies the point a very small bit. And so of course, for low values of phi, sine of phi is small as well. It's close to 0. So that means that for low values of phi, the volume described by varying the spherical coordinates will be relatively low. Whereas if you're at a large value of phi, you're down close to the horizontal. Then when you vary theta, the point is making a large sweep, around a circle that's almost as big as it can be. So when you're at a point where the value of phi is close to 90, close to pi over 2, and you're varying the angle theta, the point is making quite a large sweep. And when you vary all three of the spherical coordinates, you'll be describing a much larger volume. And of course, when phi is close to pi over 2, sine of phi is close to its maximum value, it's close to 1. So you can get a feel for the presence of the sine phi factor. Okay, so let's continue with evaluating this integral. So now I'll leave space between my integration signs to put in the limits of integration now. But the integrand will simplify a bit. We'll just be integrating k times the sine of phi. K times the sine of phi. Now I need to decide on my order. Well, I'll just stick with this order, dr, theta, d phi. Now we want to put in the limits of integration to describe the sphere. Now the question asked is to treat the sphere of radius a. So sphere of radius A, we should glance back at our diagram of the spherical coordinates. And if you want to describe the sphere of radius A, you have to think about what are the limits for the spherical coordinates. Now, when you've got the integral written down like this, you should work from the outside in. So decide upon the angle phi, first of all. And to describe points, to describe the region within the sphere of radius A, we're going to have to consider values of phi all the way between 0 and pi. The angle theta, we're going to have to consider one full sweep around at the angle theta, so we're going to go theta from 0 to 2 pi. Now, if we're just doing the sphere of radius A, then we want to consider all radiuses between 0 and out to A. Considering those intervals for the spherical coordinates, that will describe then what's going on. That describes then the sphere of radius, all the volume within the sphere of radius A. Okay. So we can now continue to evaluate this, and I don't need my absolute, I don't need my absolute values signs anymore. Well, because I'm on this interval between 0 and pi, sine of phi is always positive. So my absolute value of minus sine phi now just becomes sine phi. Okay. Maybe a small little note. And on the interval between 0 and pi for phi, sine of phi is always greater than 0. So that explains why my minus sine phi has just turned into sine phi. Now the inner two integrals you see are with respect to r and theta, but the thing you're integrating, well, k is a constant, and in terms of the variables r and theta, phi is just a constant as well. So the k can come all the way out to the front. The sine phi you can factorize that out of the inner two integrals. So even before we actually do the integration, we can simplify it to this. So then here we're just integrating 1, so we're just going to get a times 2 pi. We're just going to get a times 2 pi times k. And then the only actual integration, non-trivial integration we'll have to do is just this. It's just this one. The inner a integral, just evaluate it to a. We're integrating r. Integrating 1, the r from 0 to a. So the a goes right out to the front. The theta integral, integrating from 0 to 2 pi, the theta, that just gives you 2 pi, so I just sent that straight out to the front as well. So we've got a 2 pi k's, just integrating sine phi, so sine phi integrates to minus the cosine of phi. Evaluate that between 0 and pi. And so you get minus 1, minus 1. No, you get you get plus 1, plus 1. Cosine of pi is minus 1, so you take minus cosine of phi minus cosine of pi, you get plus 1, and then you take minus cosine of 0, so it's a plus 1. So the whole thing comes out as 4a pi k, which is what we kind of expected it. That looks like the correct form. So remember at the start we said, well, we expect some kind of formula involving the density constant k, involving the radius a, and we're integrating over a sphere, so there could well be a pi in there as well. Okay? So this is the required mass. and has the expected form. If we performed our integrals and there wasn't a variable a surviving at the end, we'd suspect we'd gone wrong. We wanted to measure the mass in the sphere of radius a, so it had to depend on it. In the same way, if the density constant k wasn't appearing in your final formula, you'd suspect something had gone wrong also. K is the proportionality constant for the density of the sphere, so surely that should be there in the expression for mass at the end. So any queries on that, or anything you'd like me to clarify from that example? So that was the example I left you with last time. It's a nice one. I mean, it takes a while to work through, but it's a good example of transferring from one coordinate system into another one. And I mean, it took us a bit of work to evaluate the Jacobian. Of course, that's only something you have to do once in your life to work out that Jacobian from Cartesian to spherical coordinates. If we had tried to tackle this integral directly here, it would have involved a lot of square roots of x squared, square roots of sums of squares expressions, which the way you actually calculate those integrals is often to bring in trigonometric substitution. So, which is in effect what we did by just transferring the whole thing into spherical coordinates from the beginning. Okay. What time is it? 22. That kind of brings us to the end of that section on changing coordinates. Is there any more questions from that section? So from section 1.17. Okay, well, in the time remaining, maybe we can look ahead into the next section then. The next section is on Green's theorem. Well, sorry, it's section 1.18 there. It's headed closed path integrals. Okay, so this is leading into the next section on Green's theorem. And you'll recall we've met two main types of integrals. Let's just focus on functions of two variables for the moment. The first kind of integrals we looked at were the path integrals, where we could integrate a linear differential form, which was a function of x and y dx and a function of x and y dy. We could integrate that along a curve in the plane, okay? So along some line or path in the xy domain. Then we looked at double integrals, where we're integrating a function over a two-dimensional subregion of the xy domain. Well, Green's theorem is something which ties the two together and establishes a link between certain kinds of path integrals and certain kinds of area integrals. Okay. So first of all, we just want to introduce the notion of having a closed path. And a closed path is, well, just what it sounds like. Some path, you can see an example there, figure 1.9 on the left. It's just some path C where the start and end point of the path is the same point. So it forms a closed loop. And moreover, a simple closed path, I think it's defined a little later on. A simple closed path would be one without any self-intersections along its length. So one without any kind of loops where it crosses itself. But if it's just one single loop without any other self-intersections, then it will be called a simple closed loop. And for path integrals along those, there's just a little addition to the notation, is that we put a little, we can put a little circle just in the middle of the integration sign, and that just indicates that the path we're integrating along is a closed one. So it's just a marker which alerts the reader to the fact that the integral they're looking at is an integral along a closed path. Okay? Because these can have special kinds of properties, so something we alert the reader to. Remember also the convention that, well, not the convention, the meaning that when you integrate along a path in the opposite directions, when you integrate along the same path but traversing it in the opposite direction, you change the sign of the integral. Okay? So that's summarized in this expression down here, where the integral along the path C is the same as minus the integral along the path minus C. The convention we had before was minus C, or C is a path, minus C denotes the same path but traversed in the opposite direction. From the end point of C back along C to the beginning point. Okay. Now there's an example shown there of a closed path integral, but I think, well, I'll work through that in detail next time. But I think we should just look ahead now to Green's theorem just to see what it's saying, and then next time we won't go through a very detailed proof of it, but I'll certainly give you some motivation and the main idea behind the proof of it, and then we'll look at some of its examples and applications of it. Now Green's theorem applies to regions that are simply connected. Now there's three examples of regions. One, okay, you can appreciate the meaning fairly easily. The top region, that shaded region in figure 11 there, is not connected. It forms two connected subregions. Okay? That's a non-connected region. But then we also have this notion of being simply connected or non-simply connected. This region down here at the bottom in figure 13 is what we call, is an example of what we call a non-simply connected region. The region as a whole is connected. It doesn't split apart into separate bits, but the fact it's got this hole in the middle of it. The holes can be quite significant in the mathematics of regions and so on. And the presence of this hole, the hole in this region, marks it as being non-simply connected. We can think of it as the boundary of this region at the bottom is not a single closed curve. It's two closed curves. The boundary of this region. You have to have the outer boundary and then the inner boundary. So Green's theorem, as we're stating it, applies to nice, well-behaved regions like that one in figure 12. Okay? A connected region, but one that's simply connected. And such a region will have as its boundary a simple closed curve. Okay? A closed curve, just one component, not two components like figure 13. Just one component. And what Green's theorem provides for us is a link between the two types of integral. Doing the path integral along the boundary of the region and doing a certain kind of double integral over the two-dimensional region itself. Okay. So what we've got on the left-hand side is a general expression for a linear differential form, p dx plus q dy, which is going to be integrated around the boundary of the region. Then on the right-hand side, we've quite a different integral, the double integral over the interior of the curve C. And you're integrating this difference of partial derivatives, q dx minus dp dy, integrating that. Okay. So it provides for us the link between the behavior of functions on the boundary of a region and the behavior of functions when you sum up the behavior of related functions, these partial derivatives, across the whole region itself. Okay. We'll work through that in detail. Next time and give some arguments for why it might be true and look at some examples and applications. Okay, so I'll see you again on Friday in this respect.